The last time I introduced this notion of a homomorphism, right? Suppose I have two groups, G with operation circle, H with operation star. If I have a function from G to H that respects the operation of the group, what do I mean by that? I mean that phi of, notice this thing in parentheses is an element of G, right? And so this operation here is the circle, right? Now, phi of G1 is an element of H, and phi of G2 is an element of H. And so the new operation here is star. It's got to respect the operation this way. If you have a function from G to H that satisfies this respecting the operation, this is called a homomorphism of groups. Now I can add other sort of modifiers, right? So suppose phi from G to H is a homomorphism. And sometimes I won't say homomorphism of groups if it's what I'm talking about is a group. We'll see there's other kinds of homomorphisms for other structures later. If phi is 1-to-1, we say phi is, well, sometimes we'll just say phi is a 1-to-1 homomorphism or an injective homomorphism. Or sometimes really want to show off our Greek roots, then we might say monomorphism. 2, if phi is onto, we say phi is surjective, if we like the French, or an epimorphism, if we like to go back to the Greek. So any of these modifiers leave that. 3, if phi is bijective, we say phi is an isomorphism. And here's another buzzword for you. Or if phi from G to G is an isomorphism, say phi is an automorphism. An isomorphism is a homomorphism from G to H that is 1-to-1 and onto. If that homomorphism goes from G to G, then we call this an automorphism. So any automorphism is an isomorphism, but the converse is not necessarily true. Can anybody give me an example of an automorphism from G to G? Notice the clue here is I didn't even tell you what G is. There's kind of a blanket automorphism from G to G that always works. Can you identify it? Identity. How about that? How about the identity function that goes from G to G? It's fairly easy to check that this is in fact a homomorphism because the operation is the same. It certainly respects itself, and this is 1-to-1 and onto. This is always an automorphism of group G. So you've always got at least that. Oh, suppose I walk up to you on the street and I give you two groups. I know for sure, there's always one homomorphism from here to here. if I give you any two groups, I don't care what they are, any two abstract groups, G and H, there's always for sure one homomorphism from here to here. Anybody care to venture a guess?
Wait, no.
What's that now?
I said G.
You know, when I tell you what the answer is, everybody's gonna go, oh. Here's what you can do that always makes a homomorphism. One thing that I know that is an H, any H, is the identity, right? Because these are both groups. Just dump everything onto the identity. And it's fairly easy to see that this is true because I don't care what these two are in G, this is the identity combined with the identity is the identity. So this always works, right? This is a rather silly homomorphism, and this is sometimes called the trivial homomorphism, where you take everything in G and just dump it onto the identity, right? But in a certain sense, this is a little bit boring, but it's there. This is even more boring, but it's there. How about some more interesting examples of a homomorphism? Well, the first thing I want to do is bring up the different operations. In fact, here's a homomorphism that you all have seen. And in fact, you all have all worked with, how many of you have worked with homomorphism properties? Okay, two of you are self-aware. That is right. Everybody has worked with homomorphism properties, but there's no shame in not knowing that because they never counted this way. There is, in fact, not just a homomorphism, but an isomorphism between these two groups. By this, I mean the positive real numbers, and I do mean positive, no zeros. Everything's positive under multiplication. And all the real numbers, positive, zero, and negative under addition. Can anybody give me a homomorphism from the positive reals under multiplication into the reals under addition? And see, we've got two different operations. Anybody want to speak up and log their guess? How about this? The natural logarithm. The natural logarithm is a homomorphism from the positive reals under multiplication into, and in fact onto, the real numbers under addition. And here's why this is true. Look at phi of x multiplied by y. This is the natural log of xy. And do tell me, dear friends, what is the natural log of x times y? What's the big thing that you always use in calculus and other places? This is the log of x plus the log of y. Agree? This is phi of x plus phi of y. So it respects, it takes the multiplication and it respects it into the addition then. I agree with that? Any questions on that? By the way, yes.
It's a late question, but in a previous example, you said that the phi of G equal to the identity of H would be a homomorphism. How can we guarantee that's one-to-one and on-to? It's all going to one element.
Oh, it's a homomorphism. It's not necessarily an isomorphism. Yeah, so you're right. There's no guarantee. It's, in fact, that one's usually not one-to-one. By the way, if you look at the graph, so this is kind of a quick way here. You all remember graphing this crap in calculus, right? This function log x satisfies the horizontal line test, so it's 1 to 1. And it's onto because the limit as x goes to infinity of log x to infinity is a continuous function. So this homomorphism is not just a homomorphism. It is also 1 to 1 and onto, right? Notice the domain of this is the positive reals and the range of this is all the reals. So there is there is actually an isomorphism of groups that goes in the other direction. Maybe I'll take a guess at that.
Exponential.
Exactly, the exponential. This takes all the reals under addition and it maps it to all the reals under multiplication. Notice that we respect the operation in R plus is addition. Pitchfork of x plus y is e to the x plus y. And what do we know about our rules of exponents? This is e to the x, e to the y. And this is pitchfork of x times pitchfork of y. And we have our new multiplication operation over here. The exponential function looks like this. Notice its domain is all the reals and its range is the positive reals. So this is also, and it's 1 to 1 and onto. So this is also group estimates. Any questions on this? Here's another one.
It's just a function.
Those are good. Let's call this, call this one tornado. Somebody at fraternity can tell me what this is. Anyway, so this, I'm going to call this GL2R. Onto. Remember what this is. This is just the set of A, B, C, D, where A, D minus B, C is not 0. So these are the 2 by 2 matrices with real entries determined not 0. My operation here is multiplication of matrices, right? There is a homomorphism from 2 by 2 matrices into the reals. What I mean here is all the reals except for 0 under multiplication, not just the positive, maybe the negative. My input is a 2 by 2 invertible matrix. Any guesses as what the output will be? Good call. The determinant. Input matrix barfs out a determinant, which is a number. And I know this number is not 0 because I'm assuming that the matrix is invertible. It's got a non-zero determinant. Let's show that this respects. This will depend on a little linear algebra. If you have 2 matrices, A and B, both invertible, this becomes determinant of AB. And what do I know from linear algebra about the determinant of AB? Determinant of A times the determinant of B, right? And this is tornado A, tornado again. So this is a homomorphism. It goes where I said to the non-zero reals under multiplication, and there's the homomorphism. Everybody okay with that? Okay. There are many, many more of these, of course. You can try to create some examples. There's a homomorphism from the dihedral group of 5-gon into S5. Actually, there's many of them. See if you can figure out one of them. Let me give you some properties of homomorphisms here. I listed this as an exercise, but we'll go through the proofs of at least some of them. Although there are. So here's some things that you know once you have homomorphism. Let phi from G to H almost always from now on, I won't bother to write down the circle and the star, the different operations for G and H. I'll write them both as juxtaposition as I have before, but of course they could be different operations. Here are some properties. Number A, phi of the identity of G is the identity of H. So this is a big property of homomorphisms. It must take the identity of the group to the identity of the target group. B. And this actually has some interesting consequences, which I will talk about later. Phi of the inverse is the inverse of phi of X. And more generally, phi of, let's say X to the n power is phi X to the n for all n z. See? If the order of X equals n, then the order of phi of X divides the order of n, or I'm sorry, the order of X. And actually, you have equality if phi is an isomorphism. D, if phi is an isomorphism, then the order of G equals the order of H. Really more of a set theory thing. And E, if phi is an isomorphism, phi is, I'm sorry, G is available if and only if H is. Okay, in particular, let's look at one. I really like one, we'll see some examples of this. I want to prove that if you have a homomorphism of groups, that it takes the identity of the domain group to the identity of the target group. So I don't know much But I know the phi of the identity of G is something in H. I don't know it's the identity of H, but I know it's something, right? My burden now is I would really like to show that A is the identity of H. Agree? That's my goal. Any ideas on how I might push this forward? Yeah.
Both sides by some element of each groups, then you can show that they're equivalent.
Right, and that's a great idea. And I want to take advantage of the fact that B is in fact a homomorphism, because that's got to be central to the issue, right? Let me ask you this. In the spirit of what you said, right? B of the identity, I mean, this is just Jim's fancy way of writing the identity. When you combine the identity with itself, you get the identity, right? I agree with that. So I'm going to take advantage of this. I know that A is this, which is this. And here's the homomorphism part. Do I agree with that? That last step is because in fact, phi is a homomorphism, so I can break this up over the two elements here. And what is phi of 1G? It's A, and this is A. So I get the equation. And this is a group, so here's where I've got checkmate. I'm going to multiply on both sides. Let's say on this side by A to the minus 1. A minus 1 times A is the identity of H, isn't it? And one of these cancels. And that's A. And that's A. So B of the identity of G is the identity of H. Everybody okay with that? Yes.
Can you explain how you went from the A equation to the identity equation?
Right here.
Yeah, and then to the line below it.
Right. So A inverse times A is the identity of H because this operation is taking place in H. Do I agree with that? This right here, intermediately, is the identity of H times A, which is A. So that gives me that A right there. Everybody okay with that? How many of you remember linear algebra? Remember when you did all that business, linear transformations? Remember that for linear transformations, T of vector, two vectors added up is T of V plus T of W, right? Everybody agree? You also had something else in linear algebra. You had scalar multiplication, right? But I'm gonna ignore that. I'm gonna forget about the scalar multiplication. A linear transformation, although they didn't put it to you this way at the time, is a homomorphism of abelian groups. The abelian groups just being the vectors under addition. When you add two vectors, new vector, you've got the zero vector, you've got the minus vector, it's associative. A linear transformation, when you did that in linear algebra, like I said, they didn't say it to you this way, but what it really is this part of it is it's a homomorphism of abelian groups. What happens when you put the zero vector in any linear transformation? What do you get? The zero vector, right? So if you have a linear transformation from Rn to Rm, if you put in the zero vector from Rn, it barfs out the zero vector in Rm. Everybody remember that from linear algebra? That's this statement right here. The identity of the first vector space, you should spit out the identity of the second vector space, right? I agree with you. How many of you all are in education? Math teaching, secondary education, so you are. So here's one for you. What is the natural log of 1? This is something you're gonna have to beat into your kid's head. Oh, you remember that? The natural log of 1 is 0, right? Do I agree with that? We all remember that? All right. Remember, the natural log from the reals under multiplication to the reals under addition is a homomorphism. The identity here is 1. The identity under addition is 0. You got no choice. The natural log of 1 has to be 0. Now, a word of teaching advice to you young folks, please do not go into your 7th grade class and say, well, clearly the log of 1 is 0 because it's a homomorphism. Don't do that. You'll lose your job pretty quickly. However, it's nice to know that that's what this, for the same reason, the exponential of 0 has to be 1 because it's the homomorphism working in the other direction. Right? Okay, any questions? All right, let's look at least a couple others of these. So I like this one in particular. So let's look at the special case of well, I want to show that phi of x inverse is the same thing as phi of x inverse. Well, let's do this. We already know this from part A, agree? So we've already done the burden of that proof. So let's write phi g, or I'm sorry, the identity of g in a fancier way. Agree? Now this is a homomorphism. Notice this is also phi of x inverse x. This is phi of x, phi of x inverse. Phi of x inverse. Great. What this equation is, that it's speaking to me. This equation is it's voices again, and what it's telling me is if I have phi of x inverse, if I multiply on both sides by phi of x, I get the identity. So phi of x is the inverse of phi of x inverse. And I can write that more succinctly as which one? No, right. And actually, I want to write it this way, so I'll put another sentence there. So phi of x inverse is the inverse of phi of x. There we go. So I can write this last sentence more succinctly this way. Phi of x inverse is the inverse of phi of x. And there you go. Are you okay with that? There is a more general statement here, which I won't do completely, but I'll tell you how to do this. if n is in the natural numbers, then inductively, you go by induction, it's pretty show phi of x n is phi of x the n power. How would you do this inductively? This is certainly true for n equals 1. For n equals 2, you get phi of x squared is phi of x times x. And because this is a homomorphism, this is phi of x, which I can write as phi of x 1 squared. So there's two base cases for you. Now go by induction, right? And the inductive step is very easy here. How do you get the case for the negative ends? Well, get this case here for the positive ends and then apply this right here. Okay. And I'll leave the rest for exercise. Note this one right here, if phi is an isomorphism, then the order of G is equal to the order of H. That's fairly straightforward because if phi is an isomorphism, it just means it's bijective, and it doesn't matter that it's homomorphism, it's a bijective function from G to H. And so by definition, they're of the same cardinality. Okay, any questions on that? Questions? Okay, we have morphisms, homomorphisms. We've got different varieties of them: monomorphisms, epimorphisms, isomorphisms, automorphisms. They have these basic properties. What actually goes in tandem with homomorphisms is another concept called subgroups. So you have two important ways to study a group. Number one is you can study it through its morphism, so its functions respect the structure from one group to another, and you can study it via its subgroups. What do you suppose a subgroup is? I mean, it's really kind of happy of me to ask you what a definition is, right? Because a definition could be anything, but if you made an intelligent definition of subgroup, what do you suppose a subgroup should be in a certain sense?
Under which the operation holds for all values within it.
Right, right. In fact, that's technically better than what I was going to say. I was just going to say parent group, a subgroup is just a baby group inside the parent, right? And that's essentially what it is. It's just a smaller group that lives inside the bigger group. Let me start you off with the following. Okay. Let's suppose that G is a group. A subset H and G is called a subgroup of G if H is also a group under operation inherited from G. That is the same operation as G. And sometimes when I say subgroup, group theorists sometimes like to watch what is the less than or equal to notation to distinguish subset from subgroup. So let's look at a couple of examples before we stampede off. Let G. Let G be the real numbers under multiplication. Can anybody give me a group? Oh, anybody give me a subgroup?
Zero.
What's that?
Zero.
Smart aleck answer. I love that. In fact, you're gonna make me go back and write something here. Any group has two sort of silly subgroups. Anybody name them?
The whole group.
The whole group and the identity, right? If G is a group, G and the identity of G are subgroups. So there's two things I can rip off really quick. So Mint pointed out that zero is a subgroup of this. That is true, right? That's true for any group. Okay, can somebody give me an example of a subgroup that is not the whole thing and it's not zero? Okay. Notice that the integers is contained inside the real numbers, and it's also a group in its own right. This thing has just a boatload of subgroups. The rational numbers is one. There's nothing special about radical 2 here. There's all kinds of real numbers I could deal with. The set of all real numbers that form integer plus integer times the square root of 2. This is a subgroup. It's easy to check. You could turn these integers into rational numbers. That's a different subgroup. This is full of. How about subgroups of Z? Notice any subgroup of Z will be a subgroup of this as well. Can anybody name a non-zero subgroup of Z? Okay. Set of all even numbers. I can trade in that even for anything I want. The set of all multiples of 7, the set of all multiples of 26, right? These are all examples of subgroups of real numbers. I'm going to go through this example quickly, perhaps. You can probably verify that my lists are complete. What if I have G as this? Under addition. Here's one sub. Here's some subgroups. Okay, so I listed the two silly ones. All of G is a subgroup, and the identity is a subgroup. Anybody find any others? If it's a subgroup, what does it have to contain for sure? It has to contain the identity. Good. So if I've got another subgroup, maybe it has to contain 0. So can anybody think of something that contains, it's got more than 0, but it's not the whole thing? Yeah.
0, 2, and 4.
Fantastic. That works.
For 2 are.
And in fact, you can check this plus this is this, this plus this is this, this plus this is this. This is a little baby subgroup inside of 3. Any others? Yeah.
0 bar, 3 bar.
He's on fire. That's right. 0 bar, 3 bar. That works. Now, here's the rub. There's only 6 elements, but it's still painful. Are there any others? Are you okay with the 0, 3?
Oh, I don't understand. I don't understand why it's just here.
Oh, because I said so. There could be others. It's just, all we need now is the 0 and 3 works, right? 3 plus 3 is 0, agreed?
Yeah.
0 plus 3 is 3 and 0 plus 0 is 0. So this is actually a little baby subgroup inside of it, right? Add two things still in there. Everything has its own inverse. This is its own inverse. This is its own inverse, right? So it's a little subgroup.
Okay.
But perhaps what's bothering you is how do you know there's not more? This bothers me too, right? Well, because you said something like, why is it only 0 and 3? Well, what happens if you throw in something other than, so let's go with that. Throw in something else. Let's throw in something else. What happens if, what if I throw in 1? What happens then? Right, and so if I've got 1 in there, what else do I have to have in there?
2 plus 1 is 4.
Right, and in particular, I've got to have, if I've got 1 in there, I've got to have 1 plus 1, 1 plus 1 plus 1, and so forth and so on, right? So what happens if 1's in there? You have to have everything. Everybody agree with that? Everybody agree with that? If 1 is in the subgroup, then you get everything in there, right? And I've already listed that, right? So I don't want 1 to be in there, right? What happens if I throw in 5? I've got the same problem, right? Because 5 is minus 1, right? So then if I have 5 in there, then I have to have 4, 3, 2, 1. So if I throw 5 into this, I get everything. What happens if I throw 2 in here? What else do I now have to have? Now I've got to have 5. And that's trouble because if you got 5, you've got everything that's already in the list. If I throw 4 in there, I've got 3 plus 4, which is 1, and I've got everything. So if you've got 0, 3, that's as far as you can go without having everything in there, which I've already listed. As it turns out, there are only 4 subgroups of this group of order 6, and you can meticulously check this. What if I group with this? Do you remember this? These are the one-to-one and onto functions from a set of 3 things to a set of 3 things. There were 6. This is the function that swaps 1 and 2 and leaves 3 alone, swaps 1 and 3 and leaves 2 alone. This one is the function that takes 1 to 2, 2 to 3, and 3 to 1. Remember all these animals? What are the subgroups of this? Again, you have G and the identity. This one's a little different because you actually, this right here is a subgroup of order 2, right? Because when I compose this transposition with itself, I get the identity. So this is its own inverse. This is a subgroup of order 2. But there's nothing special about this subgroup of order 2, so I should have 2 more. So as opposed to the previous one, this had only 1 subgroup of order 2. This actually has 3 of them. You see any other subgroups in this? Very good. There is actually 1 subgroup of order 3. We will see later that this makes that subgroup a little bit special. Notice the difference here. These are 2 groups of order 6, right? But they have different arrays of subgroups. This one has 1, 2, 3, 4 subgroups. This one has 1, 2, 3, 5, 6 subgroups, as a matter of fact, because it has 2 extra subgroups of order 2 that the other one didn't have. But notice, in both of these examples, the order of G is 6. Agreed? What are the orders of the subgroups? 6, 1, 3, 2. right? What are the orders of the subgroups? 6, 1, 2, 2, 2, 3. What do those numbers have in common? That's right. They all divide the order of the group. This is not a coincidence. And this is something we will prove later. If you have a subgroup as opposed to just a subset, any subgroup of a group must divide the order of the group if the parent group is finite order. Okay, any questions? Okay. Well, there's some examples to kind of get us warmed up. So a subgroup is just a baby group inside a group. And we are going to, I'm going to give you a proposition here. And this is often referred to as the subgroup criterion. And it is an easy way to check if a subset is a subgroup. Proposition. In my notes, there's one thing I left out. Put that in my notes. I'm assuming here in this proposition that H is a non-empty subgroup. I'm sorry, a non-empty subset of group G. Then H is a subgroup of G. If and only if for all X and Y in H, X, Y inverse is in H. And this is sometimes called the subgroup criteria. And this is a really groovy, I'm going to prove this for you quickly and I'll discuss this further, but this is just a single criteria that you can use to check. If I walk up to you on the street and give you a subset of group, this checks for you. If it give you a subset, it's not empty. This checks whether or not it is. So proof. This area, this is fairly easy. If X and Y are in H, then Y inverse is in H. So X times Y inverse is in H. Because you're assuming that H is a group, right? It's a subgroup of G, so there you go. If X and Y are in H, then Y inverse is in H, so it's fine. The interesting part is why the other direction? So why is this the only thing that you need? Well, since H is not empty, there exists X in H. Do I agree with that? We're assuming that H is not empty set, so there has to be an X in H. So, 1, X and X are in H. So X inverse, which is the identity, is in H. Right? Because we've got this, for any pair of elements, I didn't say that they had to be different. For any pair of elements, X, Y inverse is in H. So X is in H, so X comma X is in H, so X inverse, which is the identity. So H contains the identity. Ding, ding, ding. 2, since 1G and X are in H, then 1G times X inverse, which is X inverse, is in H. So now I've got inverses, right? So the subset has the identity, it's got inverses, and 3, suppose X and Y are in H, by 2, Y inverse is in H. So since X and Y inverse are in H, X, Y inverse inverse, which is X, Y, Z, H. So is closed. So I've proved that the subset has an identity, has inverses, it's closed. The associative property is inherited from G, and we're the subgroup. Any questions on it? This is a really groovy way to be able to check your groups. We'll find lots of times if I ask you something subgroup, this will be quite handy. Questions? All right, well, we will see you at least.